Good evening. Well, hello everyone. All right, well, welcome. Thank you for joining us for the 2023 F.A. Gilfillan Memorial Lecture. My name is Vaishali Bokio. I am the Interim Dean of the College of Science at Oregon State University. Tonight, we are privileged to hear from one of our esteemed colleagues, an eminent scientist who was named one of the top 1,000 female scientists in the world last year. We who are attending the lecture in person tonight are joined by more than 30 remote attendees, including colleagues, alumni and friends from OSU, University of Oregon, members of the community, and Gilfillan family members. Welcome, everyone. I will begin with our land acknowledgement. Oregon State University recognizes the impact that its land grant history has had on Indigenous communities in Oregon. We accept responsibility for understanding the continuing impact of that history on these communities. Oregon State University in Corvallis is located within the traditional homelands of the Marys River Band of the Kalapuya, who were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are a part of the Confederated Tribes of the Grand Ronde Community of Oregon and the Confederated Tribes of the Siletz Indians, some of whom are a part of the Oregon State community today. We deeply value their presence and ongoing contributions to the university and to the College of Science. It is our privilege and responsibility to support the success of students from Native and Indigenous communities throughout the United States. The Gilfillan Lecture, a long-standing tradition in our college, brings us together every year to celebrate outstanding science at OSU in honor of Doc Gilfillan, whose record of extraordinary science has positively impacted generations. Francois, Doc Gilfillan, served as Dean of the College of Science for nearly 25 years from 1938 to 1962, and as acting OSU President from 1941 to 1942. The Gilfillan Memorial Award honors Doc Gilfillan's life and recognizes his extensive service and contributions to OSU and the field of pharmaceutical chemistry. His contributions are a lasting inspiration to us. I want to thank the members of the Gilfillan family who join us virtually today for your family's ongoing investment in science, including Robert Jensen, Paul Jensen, and Kay Simon. Throughout the F.A. Gilfillan Memorial Faculty Award, you are enhancing our efforts to provide innovative teaching for tomorrow's scientists, conduct cutting-edge research, and share impactful scientific discoveries to extend the reach and impact of science for our community, Oregon, and the world. And now, I am honored to introduce Professor of Physics, Heidi Schellman, as our 2022 recipient of the F.A. Gilfillan Memorial Award for Distinguished Scholarship. Go, Heidi. This award recognizes faculty in our college who demonstrate a long and exceptional scientific career with nationally and globally recognized scholarly achievements. A trailblazer in her field, Heidi is charting exciting new territory in high-energy physics. Heidi's research impact has been phenomenal. She is a highly respected leader in experimental particle physics research, which is conducted in large collaborations where teams with diverse expertise work together on complicated problems with cutting-edge equipment that represent a significant national financial investment. Heidi's highly collaborative international research involves building very large scientific apparatus and then running them for years to get data. Since 1980, Heidi has studied the elementary particles and forces of our universe. Together with a research team from 4 universities and 3 national laboratories, Heidi leads the computing component of an international experiment called the Deep Underground Neutrino Experiment, or DUNE, to study the world's smallest particles called neutrinos. The project is funded by a $3 million grant in 2021 from the Department of Energy. Heidi has an impressive number of leadership roles that she has assumed in several international collaborations almost continuously over the past 30 years. Heidi was elected a Fellow of the American Physical Society in 1999. She was chair of the International Union of Pure and Applied Physics Commission on Particles and Field from 2018 to 2021. Currently, she is a member of the Dune Collaboration Executive Board, deputy chair of the Dune Institutional Board, and leader of the International Dune Collaboration Computing Consortium. The reason this is significant is that Dune is currently made up of over 1,400 collaborators from over 20 institutions in over 30 countries. Success in such massive collaborations hinges on detailed technical expertise, intellect, and sheer people power, all requiring strong leadership. Additionally, Heidi's leadership roles in administrative positions, including serving as department head at OSU and Northwestern, and as Associate Dean of Research and Graduate Studies at Northwestern, while leading impactful international research and strong mentoring of students in a field in which women are severely underrepresented, is awe-inspiring. Raised in Eugene, Heidi received her BS in mathematics from Stanford University in 1977, and then went to the University of California, Berkeley for her MA and PhD in physics. Her journey back to the Pacific Northwest started in 2014 after she left the Department of Physics and Astronomy at Northwestern University to become the head of OSU's Department of Physics. For her own research, she has amassed more than $4.4 million in funding since 2015 alone. Physics scholars account for 10.4% of the top female scholars, and the average number of publications for top female scientists is 547. Heidi has published more than 800 peer-reviewed journal papers. Heidi's lecture is titled, Dealing with Big Data, What to Do When Your Neutrino Detector is the Size of a Building. We are looking forward to your talk, Heidi. Congratulations on this well-deserved honor.
Okay, well, thank you for the very kind introduction and all this applause. I'm not that used to it. Normally when I give talks, I'm talking to a bunch of my peers and they just sort of, okay. Actually, I would like to point out, I didn't realize this, but this is going to come up a little later, is that Doc Gilfillan is to some extent responsible for me being here because when he was dean, he hired Ken Hedberg. And Ken Hedberg convinced my parents to move to Oregon in 1958 with me, 1 year old. They camped all the way from Minnesota to here. That was not originally going to be part of my talk, but yeah, so I'm actually a very indirect result of Doc Gilfillan being dean here. So let me see. Now I have to figure out how to run this thing. Okay, so I'm going to tell you about dealing with big data. I will comment about one thing is that in high energy physics, when we write a paper, we're a bunch of Maoists. We are all authors on all the papers. So my number of papers is actually somewhat inflated relative to those in other fields. I did not personally write all 800 papers, although I did make major contributions to most of the really cool and important ones. So, but I will say that just in general, they wouldn't have had the data to write that paper if I hadn't been around. So anyways, dealing with big data. Okay, so I was going to start with an outline, is how I got here, what a neutrino is, and how we do big science with big data. And I also have a side theme, which is how to be an athletic champion with no athletic ability. It turns out that you can actually win prizes in athletics without actually being able to do anything aside from show up. Okay, So here is actually my original Oregon State origin story, is that in 1942, Linus Pauling's assistant was drafted, and he got a hold of Glendale Community College and said, hey, do you have any people that you could send over to be my assistant? And my mother showed up. Now, you got to realize that in 1942, even Pauling was a bit surprised to have a woman show up. But he thought it was cool, and so he hired her. And he liked her work a lot, and so he promoted her. She started off at 90. I think she got up to like $120 a month by the end. Anyway, so he then encouraged her to go get her degree from UCLA and then get a PhD from Stanford, and he hired her back as a postdoc. And I will point out that Caltech, where he and she was working, did not allow women in as undergraduates till 1970. She was one of the very first women employees of Caltech, especially in a scientific role. And there was no such thing as a bad word, although there were a few anecdotes about Linus Pauling in my household. Okay. So here are my parents. This is May of '57. My father, John Schellman, was a theoretical physical biochemist, emphasis on the theoretical. My mother, Charlotte Green Schellman, was a biochemist who sequenced her own proteins and she drew her own E. coli's, separated out her T4s, and then looked at the lysozymes. So this is a very accurate picture. What is she doing? Wet chemistry. What is he doing? Contemplating. So 1 year after this, I am actually in this picture because I was born 4 months after this picture was taken. Actually 3 months, okay. And my mother generally wore very fashionable fitted lab coats. Okay, so this is me growing up in Oregon. There's me and my sister who is here. I would just like to point out, and of course, oh my God, this machine killed, these are beaver emojis. I can't believe this. I should have checked that. Dang. Okay, the duck came out fine. Okay, so anyways, I am a product of some awesome math teachers at Eugene Public Schools. Mr. Essig, 5th grade. You have heard his voice. He was the voice of Austin Stadium for something like 40 years. Our joke was that he was not using a microphone. There's Mr. Campbell, Mr. Hafner, Ms. Atwood, unknown provenance on her, and then Ms. Kimball, a very loyal duck. And I might add that I also took math classes and worked for Pete von Hippel at the U of O. And Professor Harrison was from Boston, and he kept on referring to B-Ba and C-Ba, and Mr. Fletcher at South Eugene had gone to college with him and was able to translate for me. Okay, so anyways, undergrad at Stanford. Okay, I majored in math. I took basically just took math, physics, and biology classes. The math advisors just let me run wild. Back then, there were very few required classes, and so you could just do what you wanted. I would like to thank my physics profs. Those of you of the physics persuasion will notice that 3 of these people later got the Nobel Prize. I don't know if there was a correlation. But I also won intramurals, and I learned a very interesting lesson there. I have no athletic ability, but the Junipero Ringers Association was a group of average people who discovered that they could beat the fraternities in intramurals if they just always fielded a team. And so I just went and showed up, and people defaulted. I won by forfeit most of the time. My job was I was always that person that was the extra person that showed up just in case they didn't show up with enough people. And we actually managed to win. And I was able to find the article about J.R. Ray winning in the Stanford Daily. So there it is, actual evidence that has nothing to do. This is actually physics being defeated by some other dorm. But I was able to prove that I actually have documentary evidence that I won this. Okay, so I also have documentary evidence on the next one. I went to Berkeley. My PhD advisor was George Churling. J.D. Jackson was our department head, and we had these other great physicists, Mahiko Suzuki, Andy Langford, Nigel Locker, they were postdocs I worked with, and Vera Luth, one of the physicists at SLAC. I did my research at SLAC, which is a Stanford Linear Accelerator Center, and we won the beta breakers in the centipede category. You had to have a really cool costume. Here's the really cool costume. I was actually the maintenance person. That says Acme Linux Repair. That's me. But you had to win the costume contest, and then you had to finish the race. And my job was to make certain that this thing that's made up of 30 physicists stayed together. And yes, I was doing a lot of repairs on the fly while we were running, and I had to take out Sector 26 at mile 4 when he overheated. Okay, so it's going to get less funny now. But anyways, off to Illinois. So 30 years at University of Chicago, Fermilab Northwestern, I did the E665 muon experiment. That is me sitting inside a 1.8 Tesla superconducting magnet. This is duct tape. That I am now allergic to duct tape because I did most of this myself. And this was actually a really major technical, it improved the angular resolution of the experiment by a factor of 20 or something. But anyways, this was my first experiment, well, actually my second experiment at Fermilab. So there I am, working on that one. I did these 4 experiments at Fermilab, and they all involved the interface between weak and strong forces. And I started doing a lot of computing, partially because I moved to Northwestern, which didn't have very good shop and lab facilities. So computing was something I was good at, so I did that. So this is sort of a tour, a very fast tour of what I did. So downtown Chicago, this is Fermilab. Most of those experiments were out here. There's a beam line that sort of shoots off in this way. What happens here is that they accelerate protons. They start them out here. They sort of ship them around here, and then they either ship them into here, and I always forget which way they go, into here, or they would actually put protons and antiprotons in this ring and collide them at various places around this ring. And by the way, these things are huge. This is a 4-mile circumference on this. This is what you ran around at lunch. So these are quite large, and they go up to very high energies, and there's downtown Chicago for you. Okay, so I'm going to show sort of the history of the field. We started out with groups of maybe 20 or 30. So here is the NUTEV neutrino experiment in 1996. So a bunch of people, some of them, I recognized her later on. She was an undergraduate student. I recognized her later when she's now a professor at Indiana. I think that's Ethan Siegel, the science writer for Forbes back there. I'm not certain, but I think that's Ethan. And here is us trying to return a 350-ton superconducting magnet, the one I was pictured in there. We had borrowed it from CERN, and they wanted it back. And they're still using it. It breaks down occasionally. It turns out that magnets don't like moving across the Atlantic twice. But yeah, they loaned it to the US, and then they said, we want it back. And we're going, like, where are we going to get the money to ship a 350-ton magnet back? But we did. Okay. So, and then there's the D0 experiment. This is when the experiments start getting big. The D0 experiment had about 500 people, and it ran from 92 to 2011. Here is the control room. One of the things about particle physics is once you fire up one of these big machines, it runs. My mom used to go in and you know, when she was sequencing proteins, she would have to go and sleep on the floor in the lab because, you know, every 3 hours she'd have to go and, you know, get another amino acid off. Physics, at least we have big groups. So what we do is when we're running the machine, we'll run for like 200 straight days. You know, they fill up the machine with protons and antiprotons, they collide them for a few hours, and then they refill it, and then they do it again. And you have something like 8 subsystems. Each subsystem has an expert, and that's what all these people are there. And this number of people was in that room basically for 19 years. And right now at CERN, similar, even larger groups of people are doing the same thing. So you end up doing quite a lot of these shifts. This is only a small fraction of the collaboration, but you can see it by this time. It's already a pretty international group. I worked a lot with the Brazilians and, let's see, yeah, mainly the Brazilians on the project I was working on. So Then I joined the Minerva experiment. Here's the Minerva experiment. This is an early picture when we were starting up. There's me. And this is when they were shutting down. I am not in this picture, but Maureen Sultana and Amit Bashal, which you'll see a picture of later, are in this picture. Also Laura Fields, who's now the boss of the experiment. So a former postdoc of mine who is now a professor at Notre Dame. So anyways, this was a smaller computer experiment. It's still got like 30 or 40 people analyzing the data. And one of the interesting things about Minerva is that it has a very large component of people from Latin America. We have Brazil, Peru, Mexico, Chile. The Fermilab has a strong exchange program with South American universities. So we have quite a few people from Latin America on the experiment. Okay, so after doing all this, I'm just going to skip through 30 years of my life here. Oregon State. I moved to Oregon State. I moved to Oregon State partially because of the commitment to teaching that was shown. I called up Henry Jansen. He said he was looking for a successor. I said, oh, gee, I want to move back to the West Coast. And I said, what do you guys do about teaching? And he says, we meet every week and we talk about our teaching. And I'm going, sort of sold. Because that's something you can't do at many research universities. Getting tenured faculty to talk about teaching is nearly impossible at most places. There are good places where it's not, but it's not unusual. So anyways, here's my group. The people on the top row are either graduated. Laura and Cheryl actually were paid through Northwestern, but they overlapped for about a year with me here. There's Mateus Carneiro, Amit Bashal, and Jake Capps, who just graduated last year. And Jake and Phoebe and Sean are actually in the audience today, and Noah and Maureen are off on the Zoom, I think. Maureen is actually a Rochester student, but she lives in Oregon, so she's part of our group now. So this is my research group. I'm not including the previous undergraduates. Okay, so now we're going to get down to the science. It's going to start getting boring. Okay, so what exactly do? I study elementary particles. So for a particle physicist, the chemists have their periodic table. We have a simpler periodic table. We have the standard model of elementary particles, and basically this is what we got. We have 6 quarks. We have 6 what are called leptons, of which 3 are charged and 3 are neutral. And then we have these force carriers, the gluon, the photon, the Z0, and the W, and I had to add the Higgs boson in 2012. That's why it still says new there. So what I'm actually studying is the parameters that explain the decay rates and transitions between these different types of quarks and their masses. So for example, here's neutron decay. Neutron decay, in most nuclear decays, what happens is that you'll have something like a D quark turns into a U quark and a W boson. So that's a weak interaction. The W is the carrier of the weak force. And then that W very quickly turns into an electron and an electron antineutrino. So what you've got is, you've got this transition here, D goes to U, emits a W, and then that W goes to one of these pairs here. Okay, so that's what we're doing is, in particular, the thing to realize is that the particles can interchange with each other, and that one of the things you can measure their masses, you can measure their charges, you can measure their angular momentum, and you can measure these transition probabilities. So let's look at this one. So in particular, I have studied the transition from the C quark to the D quark, from the B quark to the C quark, measured the mass of the top quark, and measured the mass of the W boson. So those are measurements I've actually played a reasonably large role in over the years. Unfortunately, I quit this field of physics before they discovered the Higgs. I went off and did neutrino physics instead. So I got nothing on this one. But anyways, these are the measurements that I've done in the standard model. And the main thing is you basically measure these transition probabilities, or you measure the masses of the particles. So the remaining thing is, let's see, I've forgotten what my next slide is. I will also just point out I am a computer nerd. I learned Fortran. My dad basically gave me a book and a yellow pad, and I learned Fortran by writing it out on a yellow pad. How many people have been to Page Springs Campground? It's the campground that's near French Glen in Malheur National Wildlife Refuge. It's like about 40 miles off the grid. So this is off-grid computing. I'm going to talk about grid computing later, but this is off-grid computing. I worked as a programmer in Pete von Hippel's lab at the University of Oregon and then at the MRC in Cambridge. I was a programmer in the beam control system at SLAC before I went to grad school. And then I ended up running the computing operations for basically almost every experiment that I've been on since then. I've sooner or later ended up running their computing operations. So I just want to point out that you now see these huge server farms. Google has, 100,000 machines someplace in Hood River or something like that. Well, this is what a really large-scale compute system, distributed computing system, looked like in around 1995. Fermilab actually started some of the first large Linux farms. People were not doing this. They were buying big mainframes. We discovered you could go to the computer store, buy a bunch of computers, put them on racks like this, and you could get a supercomputer, what was a supercomputer back then, really quickly. Okay, so that's one of the things we did. We had to make things run on Linux. You wanted to have a nice, cheap, free operating system. That way they couldn't bill you for the operating system. And then we actually started working on a data access system, which turned out to really work quite nicely. It's actually a precursor of all these cloud storage things. What happened in our case is that when we wanted to process a file, we would ship it off to some place like Wuppertal in Germany, and we'd process it there. And then 2 weeks later, we decided we wanted that file again. It turns out it was still in Wuppertal. So we sort of accidentally discovered distributed computing. The idea was we were just going to bring the data to the job, but since we left it there and we could find it again later, we had it's like Box where you know exactly where things are. It worked pretty well, and we're still using it. We're trying to replace it, but that's a piece of code that's actually lasted almost 25 years. Okay, so my favorite particle is the neutrino. I'm going to check my time here. Okay, the neutrino has very low mass. It's like 1/1,000,000th of an electron mass, probably. It has no charge. It's stable, as far as we know. We don't see them decaying. And it couples only via the weak interactions. Well, maybe since it has a little mass, maybe gravity works on it, but it's pretty hard. It's very hard to detect because it only interacts through the weak interaction. And actually, I brought some neutrinos. Here's some neutrinos. These are the mixed neutrinos. I'm buddies with the particle zookeeper. If anybody wants particles, they can buy them. They're actually available online. Here are the unmixed neutrinos. You'll see this later. These are actually Christmas ornaments. That's what's on our tree. Okay, I'm just going to make an apology to everybody. You're used to using joules or ergs as your units of energy. We're particle physicists. We use something we can actually measure. We use something called, chemists do this occasionally, electron volts. We use electron volts as our energy. It's basically, we're moving around singly charged particles, and we use big voltages to accelerate them. So if you put a 100 kilovolt electric field on something and it's got a charge of 1 electron charge, you end up with 100 electron volts of energy. So that's how we do our units. And so we transform everything, the mass of the proton, the mass of the electron, everything is translated into these energy units. And don't even ask me what h bar is. It's a lot easier than the real one, because it's like 197. Okay, so I would just like to point out, I have a table here that sort of tells you. So I'm mainly going to talk about MEVs and GeVs, which are the energy scales for nuclear decays and particle masses. The big LHC accelerator at CERN is up in the TeV, the tera electron volt. But occasionally we do deal with real electron volts because we're dealing with individual atoms and things like that. So, and also thanks to Dr. Tenbrink, my 11th grade physics teacher, who taught us about units very thoroughly. Okay, so one thing about neutrinos is that when the Big Bang happened, most of the particles went off and annihilated with their antiparticles. But in fact, the neutrinos, many of the neutrinos ended up basically being left over. And there are 337 neutrinos per cubic centimeter left over from the Big Bang. That's slightly fewer than the photons left over from the Big Bang. If you've heard of, well, the cosmic microwave background, there's also a cosmic neutrino background, which nobody's ever seen because they're really hard to see. The sun hits us with about 10 to the 11th neutrinos per second per centimeter squared. And in fact, if you have a large enough neutrino detector and you wait long enough, you can actually see, you just look down with your detector and you can actually see the sun in neutrinos. So this is a picture of the sun taken through the Earth in neutrinos. So the good news is if the neutrinos ever stop, we'll get some warning because this detector will tell us the sun has stopped working long before the normal signal would propagate out to the edge. This is looking, by the way, this is looking right at the core of the sun. We look at the surface in light. This is the core of the sun, but the resolution isn't good enough to see it. Okay, so a supernova can actually produce up to 10 to the 58 neutrinos. Most of the energy from a supernova is going to come out in neutrinos. And also, of course, natural radioactive decays also produce neutrinos. But anyways, at any given moment, there's a heck of a lot of neutrinos in you. Okay, so why study them? Well, they directly measure the weak force. They played a very major role in the early universe. And in particular, any difference in interactions between neutrinos and antineutrinos could explain why there's more matter than antimatter. I'll go do a little bit more on that later. That's one of the things we're really looking for is, do neutrinos and antineutrinos act the same way? There's some evidence that they don't, and that's a major thing that we're trying to do with the Dune experiment. Neutrinos are really cool. I mean, you know, they're not garden variety particles. Though the problem is they're really hard to detect. You can instrument 800 tons of material, aim a beam of neutrinos at it, and you only see 1 in 10 to the 12 of the neutrinos. The tau neutrino, which is really hard to make, was not seen in a lab until the 2000s. And until 1997, we had no indication that they had any mass. And now I'm going to explain a little about how we detect them and then how we know they have mass. So, how do we detect neutrinos? Okay, so once again, the only thing you can do, these things don't interact much, so you've got to have a lot of neutrinos and a lot of stuff. You need a whole bunch of material. So this is an example of the Super Kamiokande experiment, and right now it's not full. This thing is almost 40 meters high. It's that's the diameter. It's 40 meters across, it's 40 meters high. So basically just sort of think about this room, but much larger. It's completely coated with these big photodetectors, and then they fill it with purified water up to the top. So you have, many tons of liquid water, and if a neutrino comes in and interacts with that, it will emit a very small amount of light, and these very sensitive photodetectors will see it. And that's actually the experiment that made the picture of the sun that I showed you earlier, because they can see solar neutrinos. It has around 11,000 electronics channels. The problem is it's sort of coarse-grained, so it can't see the real details of an interaction, but boy, can it see a lot of interactions. And they're in fact building one that's like 20 times larger than this right now. So how do you make a neutrino beam? Well, actually the atmosphere does it for you. Protons come in from cosmic rays, hit the top of the atmosphere, produce short-lived particles that decay to neutrinos. And so, in fact, there's neutrinos and muon particles and other stuff showering down on us from above. But we do that on Earth by taking protons from you basically build a very large proton accelerator. Okay, so, and then you hit a target with those protons, and they produce a small number of other fundamental particles, for example, pi plus and pi minus mesons, which are combinations of quarks, which I'm not going to go into detail on. But those particles then decay into muons and muon neutrinos. So what you have is, if you whap this target with a proton, you're likely to get a muon neutrino that is kind of, sort of, maybe going in the right direction. You can make it go more in the right direction by putting in magnetic focusing elements here, which focus either positive or negative charges. That's how you choose neutrino or antineutrino. But once it's done this decay, you can't steer those things. How do you steer something that doesn't have a charge? One of the problems with neutrinos is not only are they hard to make, they're hard to detect, and you can't steer them either. So anyways, what you do in order to do one of these measurements is you basically do this every second, bop, focus, decay, and you do have to filter out all this other stuff. So you basically put a few 100 meters of rock, and you put your neutrino experiment out here. You do that every second for 5 to 10 years, and in the end you end up with maybe a couple million interactions. Okay, so now it gets complicated. The easiest neutrinos to make in the lab are muon neutrinos. A little strange. That's that we ask people that on their thesis exams, but you make muon neutrinos. But if you make a beam of muon neutrinos and let it go far enough, you start seeing tau and electron neutrinos, and that was a big surprise. That was actually discovered in 1997, and the 2015 Nobel Prize was awarded for experimentally observing this effect. So what the heck is happening? And now Liz Jerry is going to start throwing things, as is Ken Crane. So one thing is that particles actually can act as waves. If you took Physics 314, you know this. We don't offer that course anymore. Okay, so here it is. The wavelength of the particle depends on its velocity and its mass and Planck's constant. So if two particles have different masses and they start off at the same point and they arrive at another point at the same time, they have to have the same velocity. But if they have different masses, they're going to have different wavelengths. So you can imagine that, they're just going to be at different phases. Now, if there were no quantum mechanics, you wouldn't care what their wavelength was. But in fact, you can have superposition. So I'm not killing any cats here. Okay, so here's the deal. You have a cat. You open the door for the cat. Is the cat going to go through the door, or is it going to stay where it is? You don't know. It doesn't know. It may take quite a while for it to decide. So I'm assuming that somehow cats actually exist in a superposition of in the in state and the out state, and some random cosmic ray hits a neuron, and at that point the decision is made, the wave function collapses, and it makes the decision and walks out the door or stays there. Okay, I've just butchered quantum mechanics. But anyways, the thing is that things can exist in sort of these indefinite states that are superpositions of two other things. And that's what these guys are. This is, I think, a muon neutrino, and this is the M1 neutrino, which is, this one is guy here is a superposition of, well, it looks like mainly, actually he looks like it's mainly superposition of this guy, but with a bit of this and a bit of that. And it's kind of like if you're looking at polarized light, you can think of light that's polarized at 45 degrees as being a superposition of light that's polarized this way and light that's polarized that way. For the mathematicians in the audience, we're just using a different basis for our vectors. I think of this as the mass basis. This is the mass basis. This might be the interaction basis. So let's look at this. Our neutrinos, when they interact, they're described by their electronness. This guy likes electrons, this one likes muons, this one likes taus. That's great. But when they move, they're described by their masses. And the mass eigenstates, these guys, are a combination of these guys, and these guys are a combination of these guys. So in order to understand what a neutrino is doing, you actually have to look at it, sort of switch your point of view on it as it moves along. So here's an example. If you start out with a muon neutrino here, that muon neutrino can be thought of, this is just if there were only two flavors, you can think of it as being a linear combination of a nu 1 and a nu 2. These are different mass states. So the muon neutrino is some combination of these guys, and there's a mixing angle that tells you what that combination was. In the case of the cat, it was a square root of 2. So it starts out sort of being half one, half the other, but because these guys have different masses, they will have different wavelengths. And so as you go along through space, those waves will get out of phase, and it's possible to end up with a phasing that gives you the combination that gives you an electron. And in matrix form, you basically start out with this guy here, you rotate it into the mass basis, you then propagate the mass basis based on the masses, and then you propagate it back, and you get a different combination. So it's, this is, we're not going to do much more on this. There will not be a test. Okay, so it gets even worse. In reality, there are three kinds of neutrinos, and they have a three-flavor mixing, which means that you basically end up having, it's a 3x3 unitary matrix, and 3x3 unitary matrices can have complex phases in them. This is kind of interesting because that phase actually flips between matter and antimatter, and don't ask me why, but it does. Some of the angles here, this is like the cosine of angle 2, 3 and sine. Some of these angles are quite large, some of these angles are quite small, but they're all finite, and what that means is we don't know what this phase here is, but everything else we know is finite, and we've actually measured it in the lab. So the question is, do these terms show up? Because if they do, then there's an asymmetry in the way neutrinos and antineutrinos interact. Okay, so I gotta look at my watch, make certain I'm not doing too, okay. So anyways, neutrinos are described by their interactions or by their masses. So here they are here. Here's that mixing matrix that tells you how they work. They're just two different views of the same neutrinos. So what we're going to do is we're going to try to measure that complex phase. We're going to make a lot of neutrinos. We're going to build a detector 1,000 kilometers away. We're going to measure the neutrino conversion rate. We're going to measure the antineutrino conversion rate. And we're going to compare the two. And if they act differently, we have a clue actually about the early universe. Because in the early universe, down here, all the particles were around. All of these guys, if you go to an early universe, energies are really high. And all of these particles are floating around, and they're all bopping into each other and annihilating and then recreating each other. As the universe cools, these particles either decay or they find their opposite numbers and they annihilate. But the neutrinos tend to stop annihilating pretty late in the game, well, really early in the game. And so you end up with a universe that's basically full of U and D quarks, electrons, and all the neutrino types, and photons. So that's what you have. So they start out here, and exactly how this evolution occurs is very strongly influenced by the number of neutrinos and the types of neutrinos. And in particular, if neutrinos and antineutrinos interact differently, you're going to get a different evolution of the universe. You're going to get a different set of particles that we would see now. And in particular, the real surprise is, considering that we think that the universe was reasonably symmetrical at the beginning, why is there any matter left? Because you would think all of it would have run into its antimatter and wiped itself out, and all we'd have left would be photons and neutrinos. But that's not true. And that's a hint that there's some kind of asymmetry between the way neutrinos and antineutrinos interact. And that's what we're looking for. So, it's, why we're here. Okay, so, but this is not easy. You have to go a long distance, you have to have a really strong neutrino beam, you have to have a really big neutrino detector, and you need a lot of people and dollars. So here is our technical solution. It is something called a liquid argon time projection chamber. And here it is. Let's see, let's go back. Okay, so you have an interaction here. And that interaction actually, particle interaction ionizes the argon. And there's a very strong electric field. And the electrons are going to start drifting towards this wire plane here. And when the electrons reach the wire plane, you can sort of see them reaching it at various times, they're going to deposit energy, and you get a signal on the wire plane. So this requires very, very clean argon. You have to use a noble gas, because otherwise any chemical impurities in this are going to just grab onto the electrons and never going to be. These things are going like 3 or 4 meters. So you're actually having to drift an electron 3 or 4 meters in a liquid. So it has to be a pretty noble gas. So that's what's going on here. This is actually a result. The resulting picture that you get if you have very closely spaced wires. This is, I believe, from the Protodune experiment at CERN, which is one of our prototypes. And you can see particles coming in, and you can see them interacting, and you can just see this huge amount of detail coming out. So this is what we're going to use to try to measure the difference between, for example, neutrinos and antineutrinos. I'm going to skip some of the technical details. This is one of those guys under construction. These things are big. They're like 6 meters long. Each detector plane is like this. The picture I showed you, and I was only showing you a small part. So if an electron neutrino comes in, it's going to hit a nucleus, and it's going to produce an electron. So that's what's happening here. That's an electron. Electrons basically interact with anything. They just blat away like this. If a muon neutrino comes in, it will actually scatter off a nucleus, and this picture could have had these guys in it. But the muon particle actually does not interact that way. It just sort of wanders along until it deposits all of its energy sooner or later in the argon. So the scales here are of order of a meter. So that's the scale you're looking at this, but you can see that there's actually incredible detail. You've got detail on the millimeter scale in these pictures. And that's good, because we really do want to be able to tell these things apart. Okay, so what we're doing is we're basically building a huge liquid argon detector called DUNE in the Homestick gold mine, and we're making a very powerful neutrino beam that will run for 10 years. Okay, so I am going to skip a bunch of pictures, because so this is this is the top of the shaft that goes down into the mine. It is, in fact, a mile down. We are building large caverns which are going to contain these big detectors. And this is detail of what those look like. These are boxes are going to be the liquid argon detector. There's going to be, electric fields across these guys. And this is what they actually look like. I'm going to keep zooming in here. These things are 19 by 18 by 66 meters long. They're not each the size of Wenneker, but if you stacked all 4 of them together, you would get something the size of Wenneker Hall. So this is what I mean by big data. And just remember that I was showing you detail on the centimeter scale here. So when you're reading these things out, you're reading something out that's about the size of this building, and you're reading it out with data on this scale, which means there's a lot of data there. So there's a close-up of what it looks like inside. There's, once again, here are those big wire plane detectors. These are the actual detectors. They're hanging. So this guy here, which I showed you earlier, is actually this little thing there. Okay, so what we did do is we built some small prototypes at CERN. We wanted to test this. We're not going to run the big one until the end of this decade, but we've done a test. So we built these very nice 1/25th prototypes, ran them at CERN, and I will just point out CERN is very nice. They have, you can see the Mont Blanc from the cafeteria. The food is excellent. The pastries are amazing. There is a line for the coffee machines, and sometimes it's password protected. Here's one of those prototype detectors. Now remember, this is a 1/25th scale prototype, and there's some people over there. And we ran it in a beamline. We put 6 of those guys inside that big red box, and then we filled it with liquid argon. And here is actually the filling it with liquid argon, which took several weeks. And then you have to purify it for several weeks as well. So for those of you of the physics major persuasion, this is why you have to take E&M. The good news is the volume is filled with a uniform material, so simulating what goes on in there is easy. The bad news is that you have to deal with the liquid actually charges up. There's enough particles going through it that it charges up. So you have a charged fluid in a non-uniform electric field, and that charged fluid is moving at a few centimeters a second. So you have to worry about how does it flow, where's it flowing from, and figuring out the field lines. And our postdoc, Jake Calcutt, has to worry about that. He's nodding, yes. Okay, so this is what the data looks like. We actually only took data for 6 weeks with Beam. We also took a lot of data later. If you look at this in very great detail, you can see there's actually the beam comes in here and there's an interaction right here. The rest of this is cosmic ray muons coming down from the sky. There's like 60 interactions coming from space at the same time that we have our very powerful beam line giving us this one interaction here. So we read out 8 million interactions over those weeks. That was 400 no, that's wrong. It was 400 terabytes of data. I always get this wrong. It was 0.4 petabytes of data. We've also generated a lot of simulation, and we've also reprocessed it something like 4 to 5 times. So at this point, we have something like 20 petabytes of data floating around. This is what one of those events looks like. Once again, showing the kind of detail that you get. And this is actually a pi-0 particle that can mimic an electron, but the way you can tell that it isn't an electron is it doesn't start here, it starts later. So that's an important thing to do. Here's signal processing. You basically start out with data that looks like this. You do all sorts of convolutions on it, and you end up with something like this. Once again, still very complex because it's got all these extra particles floating around, but that's how you do it. This is what a single channel looks like, is you get quite a few blips. Okay, so the current status is we're now building the full detector. So once again, reminding you about this guy. The cavern is under construction. Most of the rock has already been removed, so we're going to be done digging the hole by the end of next year, and then we're going to start building those detectors in it. Here's how the neutrinos go. They go this way. That's very similar to the flight path. We fly over this on our flights to Chicago. This is how the data is going to come back. It turns out there's no direct 100 gigabit per second line from South Dakota to Chicago. And in fact, we're having to pay to get one installed, which will probably help the local school system. So the plan is going to be to actually write about 30 petabytes of data a year, mainly for calibration, but we will see a reasonably large number of these neutrino interactions. And the bottom line result we're looking for is if matter and antimatter behave the same, you would get this black curve. If they are different, you might see this and this. In other words, antineutrinos would go down, neutrinos would go up, or possibly neutrinos would go down, antineutrinos would go up. This is simulated data after a few years of running. And so those blue and red curves are the evidence that we would be expecting to see of possible matter-antimatter asymmetry. But wait, there's more. If you instrument this much stuff and put it in a mine, you can do astrophysics. In supernova 1987A occurred in the Large Magellanic Cloud. And at that point, people had just turned on a neutrino detector, the first big neutrino detector. And they saw a signal. They saw something like 15, 20 neutrinos out of that thing. And that was huge because it's like, whoa, people did not expect to see this. And of course, we haven't had another supernova since then. But if a supernova occurs now, we expect to see a signal that might be this green one or this red one. We don't know yet over the first few seconds. And in fact, that signal extends over many seconds, and it tells you many things. It tells you how did the supernova work? I mean, what's the mechanism for the supernova? And the other thing it tells you is, for example, where was that new supernova? Not all supernovas occur where you can see them with your eyeball. They might be in a gas cloud. They might be behind something else. So this is what supernovas in Dune would look like. So by the way, look at the scale on this. These are, these things will go about, the signal from the supernova is going to be a bunch of little blips about this long in that detector. But there may be hundreds, there may be thousands, there could be close to 1 million, depending on how close that supernova is. And so it'll light up like a Christmas tree, we'll read it out, and we'll be able to tell the astrophysicists which way their neutrino is, or their supernova is. So Dune should be able to see if we see another supernova. The bad news is these things happen every 30 to 200 years. We got lucky last time. We may not get lucky again. The problem for us is that if we read out the whole thing, we have to move 600 terabytes from South Dakota over a reasonably slow internet length. So just a picture is the data I was showing you earlier is like one of these trucks. That supernova data looks like this. And so we're getting ready. We've got all the collaborators. Once again, we always need lots of people. Some Oregon State CS students made this nice diagram that shows all our computing centers and the data traffic between them. So we have computing centers all over the world, and we distribute our data, and we process it worldwide. This is one of our, not the largest computing center. It's the CERN, actually probably is, the CERN Computing Center. They're building a new one. This is jobs running. When we were doing heavy-duty processing, we sort of fired up, and for about a week, we ran on between 5,000 and 10,000 cores. Google does that before breakfast, but it's quite a lot of computing. We have a tape robot. Actually, there's 5 of these babies. There's 12 terabytes per tape, and there's 10,000 tapes in the robot. You have this robot that runs back and forth, grabs tape, sticks it in a tape drive, and puts it back. I'm going to skip that one. I'm just going to say, actually, I shouldn't skip that one, because this shows you the contributions. These are international contributions. We used 48 million wall hours last year. We're going to use more when we're really running. And the main thing is that the US was this green thing here. The UK, CERN, the Netherlands, Spain, and a whole bunch of other countries contributed a very large fraction of our computing through a computing consortium, and the storage is also highly distributed. Okay, so I'm going to finish up by having a supernova. Okay, so Betelgeuse, a mere 642 light years away. If this guy goes off, it's going to be big. This is because this thing is really close. The calculations I showed you earlier were for a factor of 20 or 30 further away than this. So, and it's been acting really wonky recently. People think it's going to blow in the next 100,000 years. But, hey, there's a lot of excitement. It's like, hey, this thing's acting strange. So my conclusion, I'm going to conclude now. I've gone through everything. You've learned quantum mechanics, E&M, matrix algebra, etc. Conclusions. Dune is on track to start at the end of this decade. We've tested all the technology. Lots of trucks of argon are going to start heading for South Dakota soon. We should be able to tell the difference between the red curve and the blue curve, and the black curve. Is this the reason there's more matter than antimatter? Is this why we're here? And then finally, we humbly request that dang star does not go supernova until we turn on. It's got to wait about 10 years. It would be so frustrating if that thing blew up. Okay, so thank you. I'm ready for questions, and sorry for going over a little.
Thank you so much, Heidi. That was, wow. You are one funny lady. Who knew? I'm Virginia Weiss. I'm the acting associate dean in the college, and we're going to take some questions now. And it's super important that you use a microphone because we do have folks joining us online. So please raise your hands, and we'll get the microphones to you.
Hi, Heidi. It's Jeff. I'm over here.
A real astrophysicist.
No, I have a simple question, I think. Where do you get that much argon, and how much does it cost per gallon?
Okay, the good news is it doesn't, there's a short-term answer, there's a US answer, there's a European answer. So, argon is actually about 1% of the atmosphere. And when they make oxygen and argon for iron production, it's a byproduct. And so it's produced pretty commonly. And in fact, I think it's something like maybe $1 a liter. Now, remember, there's a lot of liters there. The problem actually is that in Europe, energy costs went up enough that they stopped making iron. And when they stopped making iron, they stopped buying oxygen. And the price of argon right now is like a factor, spot price is like a factor of 50 higher than it normally is, which means we're trying to do another prototype run, and we are stuck because we cannot get the argon. It is a worry, but I always, when I'm reviewing an experiment, I always check the commodity price and what fraction of the world's supply we're going to be using. Because yes, particle physics is like you look at it as, hey, we're going to build this out in niobium. It's like, well, that is 3 years production of world production of niobium. That sounds difficult. Actually, another thing on that one, I heard from somebody that xenon is also a byproduct of the same process. And it turns out that satellites use xenon gas to do their, little rockets they shoot out because it's really heavy. And the xenon spot price is insane. So, in fact, Boeing is having trouble getting it for their rockets. So yeah, go buy, no, don't. I'm not giving stock advice, but yeah, hoarding noble gases might not be a bad idea.
I have a question.
Oh, he always has a question.
So given the interesting matter-antimatter asymmetry question, but the difficulty of detecting neutrinos, why don't we just use electrons and their antiparticle protons and do a laser spectroscopy experiment? It'd be a little cheaper.
Yeah, people are doing that. Actually, I don't know if anybody can see CP violation. I know we can do people do parity violation all the time. It's you have to do both, but this is getting technical, but you have to do both parity and charge conjugation violation. And I don't think anybody has ever seen CP violation. They've seen it in quark decays, but it has to be the weak interactions, and that's a very interesting experiment. Let's go write a theory paper. Yeah.
There's a question from someone online, Alyssa Dirks. She wants to know, is there any indication that neutrinos might do a random walk as they are traveling through the Earth, energy exchanges interacting with anything else?
Well, yes. There's actually, that's one of the things I skipped over is that, in fact, when neutrinos pass through matter, they don't completely not interact. Electron neutrinos pass through matter slightly differently than the other ones because they can have an additional interaction with the atomic electrons. If it's a muon neutrino, it's going through matter. There are certain interactions, and that has a very subtle effect on the propagation of the particles. So yes, they do a random walk, but they still go in a straight line. They're just affected, they are affected by going through material, but very slightly. Is there another question from online?
I can't ask you any physics questions, I'm sorry.
Oh, yes, you can.
There's physics, and then there's chemistry, and there's biology, right? Okay.
Listen,
but I will ask you a question about women in science. And so clearly you had a wonderful role model in your mother. And, but nonetheless, you entered physics at a time when there were few women, and indeed there still are not, it's not half and half, let's just say. So how did you navigate that? Did you feel there were barriers, or did you feel that you had a path that was easier than you might have thought it would have been?
Well, maybe I should talk a little about, this is an anecdote from grad school, is that, I was the daughter of two, basically, I don't think they described themselves, very feminist chemists. My parents did a lot, they didn't do completely equal housework, stuff like that, but they were very egalitarian in the way they worked. So I was raised by people who basically just expected I could do anything I wanted to. So that made a big difference. But I will tell you a story about, I'd say, privilege in grad school. So in grad school, there were 19 women and like 400 guys. And the 19 women would get together at somebody's apartment, like Persis Drell, who just stepped down from as being provost at Stanford, or Margie Shapiro, who ran the physics department at Berkeley for many years. But anyways, we'd get together, and I went back and I looked through those women, and I said, what do I know about these women's backgrounds? And as well, it turned out that of those women who were meeting in that place, 3 of them had fathers who were in the National Academy of Sciences. So in other words, the women back then, the survivors, often had incredible family support. So I think that's something that's sort of changing. As more and more women can go ahead and succeed in professions like being doctors, lawyers, etc., I think it's a lot easier for people to have I'd say the cultural capital that it takes to survive. But yes, my generation were very good, but they also had huge advantages in going into the original, going into grad school, and huge family support, I think. So be nice to your daughters. Being rich and famous also helps.
You may have mentioned this and I might have missed it. I've heard that there's evidence that when a supernova occurs, that the neutrinos reach Earth, reaches before the light does. In other words, somehow the neutrinos are ejected before the big explosion happens and then the light comes. Does that sound true to you?
Yeah, it's actually true. I mean, some of it is. The main reason is the neutrinos, just like with the sun, the neutrinos are coming out of the core. And it actually takes a while. The light you see is from the surface, and it takes a while for just the shock wave to reach the outside. Excuse me. I mean, you also see this with like the neutron star merger that happened a few years back. Actually, LIGO's turned on again. They've already seen something yesterday. So keep your eye on that. But gamma ray bursts, like when the neutron star merger happened, I believe that the gravitational wave signal, which travels at the speed of light, reached us about a second or two before the gamma ray bursts, which are from a very small region. If it's a neutron star merger, it's really small. One of the things is in principle, if the supernova is far enough away, the neutrinos do have a slight mass. And one of the best limits on the masses of neutrinos was actually set from that supernova in '87, because you would say, hey, listen, they all came within a certain amount of time, and that gave you some idea of the range of masses that neutrinos could have, at least the range of mass differences. Now that's been superseded, but there is information about the mass of the neutrino. But yeah, neutrinos, one of the things that's great about neutrinos is they're actually telling you what's happening at the center of the supernova, not on the surface you can see. And if it happens in some place that's all cloudy and messy and dusty, there may be supernovas happening that we don't see because they're hidden. And these neutrino detectors would be the only way of seeing them. Oh, well, I guess the gravitational waves, maybe.
Another question from online, Robert Avery. Has CERN or Fermilab, et cetera, considered peer-to-peer storage and distribution of the experimental data?
That's, okay, maybe, I'm not certain really, I mean, that's sort of what we do. We basically have a system called Rusio, which moves data around, and we run our own. One of the problems with particle physics is we're cheap, and we want to get this stuff done, so we've often developed our own systems for doing this. We don't store things on your personal laptop or something like that. But the storage that I showed is spread across at least 10 data centers. And in the past, we used to just plunk the files all over the place. One problem we do run into is this is generally, it's open source, it's fully documented. I just came back from the conference where I got a cold. And what we found is that commercial vendors, sooner or later, they will take your money. So the main thing they do is you send your data off to Amazon Web Services, and they don't charge you much for the processing, and they charge you a lot to get it back out again. Whereas when we set things up, we own our disk, we move stuff there, and we don't charge each other for it. As I said, we're a bunch of Maoists.
This is kind of related to that. Have there ever been cases where you generate too much data that you don't have enough storage for, so you have to get rid of it, or is that not an issue?
We do that all the time. I mean, actually, the neutrino experiments, in our case, we're actually probably writing everything out. That's why I have that huge 30 petabytes. The CERN experiments actually generate data at huge rates, and they don't write 99.99% of it. They have whole decision trees as they look at the data once and they say, well, is this worth looking at? Nope. And then they go to the next level, and we did the same on the D0 experiment. These big collider experiments generate data at huge rates. And in our case, we don't have to record the data. Well, if a supernova happens, we have to be able to tell it happened, and then we'll read the whole thing out. If we read this whole thing out all the time, we'd be reading at 10 terabytes a second. No, is it 10 terabytes? Yeah, that's close to 10, like 5 to 10 terabytes a second. Nothing can stand that, but we're not doing that. So yes, we always have to make those kind of selections. We have to make some kind of clever decision. You have to do data compression, or you have to just decide what you're interested in, and you can miss things because you have to have made that decision ahead of time.
Heidi, you mentioned Fortran at the beginning. How is the language, the computer language, developed? Is the code still stuck way back, or has the code been rewritten in all the new different languages, or how does that work?
Well, I will say that in 1995, when I was starting to be in charge of things, there were certain people I didn't want coding anymore, so we went to C++. So we do most of our algorithms are now written in C++. Some people use C. We use C++, and people are moving towards using Python. At the conference last week, there was a huge Julia contingent, but nobody teaches that, nobody learns it. I will say, I'm hoping that CS here starts teaching people Python instead of C++ as the intro class. And from a physicist, that's really pretty blasphemic, because we need the C++ to have the algorithms run quickly. But yeah, we fight over languages all the time.
Okay, it looks like there's one final question from online, and then we'll wrap it up.
Leah Holmes wants to know, why does the electron neutrino scatter and the others don't?
Okay. Hi, Leah. Leah is I think she's in Virginia. I think she's starting grad school next year. She was an undergraduate doing research in physics last year. So hi. Anyways, so what happened? Let me think about this. So as an electron, muon neutrino, it's passing through the Earth. It can sort of do something where it emits a Z0 boson and interacts with an electron through the Z0. That's how it works. Okay, so it can interact through a Z0 boson. It can sort of do something like this. It goes blip to an electron, and then it keeps going. The electron neutrino can actually either, if it's an electron antineutrino, it can actually annihilate with an electron into a W boson that then changes back into an electron antineutrino and the electron. So there's two different interaction types that you can have if it's going near an electron. Whereas if it's a muon, it really only has one interaction type.
Okay, Heidi, you are a treasure for OSU and the college, and that was just a wonderful sort of romp through particle physics. And join me in thanking Heidi again, and congratulations.